Section 1.9, Inverse Functions. Don't ever doubt your worth. Unknown. So today we're going to talk about inverse functions. Let f and g be two functions that f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f. So here the important thing is that if you take the composition, then you get x on both compositions. The function g is the inverse of the function f and is denoted by this symbol, f inverse. Thus, f of f inverse of x is equal to x, and f inverse of f of x is equal to x. So if they're inverses of each other, you're always going to end up with x when you take the composition. The domain of f is equal to the range of f inverse and vice versa. If a function f is a set of ordered pairs x, y, then the changes produced by f can be undone by reversing the components of all the ordered pairs. The resulting relation, yx, so the x and the y were reversed, may or may not be a function. In this section, we will develop those ideas by studying functions whose compositions have special undoing relationships. The definition of the inverse tells us that the domain of f is equal to the range of f inverse, and vice versa. This means that if the function f is a set of ordered pairs x, y, then the inverse is a set of ordered pairs y, x. So for example, if they give me that the inverse is, find the inverse, and they give me the function f, and these are the ordered pairs for f, then by the definition, f inverse is going to be the ordered pairs with the x and the y reverse. So instead of 4, 2, we would have 2, 4, 3, 9, 6, 36. And this would be your inverse. Number 2, which of the functions is the inverse of f of x equals x minus 4 divided by 7? So if we want to know which of these is the inverse, and I went ahead and added a third option, then if we take the composition as stated up here, we should end up with x. Okay, so we can start with the first one. We're going to find g composed of f of x. If it's going to be an inverse, then it needs to give us x back. So here I would have g. F of x is x minus 4 divided by 7. Now I'm going to plug this into the function g. Okay, so I plugged in x minus 4 divided by 7 into this x. And now I can simplify. On the top here, I need a common denominator of 7. So in order to make this 2 have a denominator of 7, I will need to multiply the top and bottom by 7. 2 times 7 is 14, and this is all divided by 5. So in the top numerator, I can now get x minus 18 divided by 7. Minus 4 minus 14 is negative 18. And then this I can rewrite as x minus 18 of 7 times, or I'll just write it as division, divided by 5. And I'm going to come back up here. So x minus 18 divided by 7, I can change that to multiplication if I take the reciprocal of 5. So we get x minus 18 over 35. So the answer for g of f of x is equal to x minus 18 divided by 35. Since we didn't get an x, then that means that this is not an inverse of f of x. If we did get an x, then we would have to check f composed of g of x to see if that also gives us an x. Okay, so both have to give you an x, g of f of x and f of g of x. If one fails, then you can stop and say that it's not an inverse. So let's check this one, h of f of x. So I'm going to plug in f of x here. So I get h of x minus 4 over 7. And anywhere I see an x, I'm going to plug in what's in the parentheses for h. So we get 5 over x minus 4 divided by 7 plus 2. I'm going to take care of this here by dividing. So 5 divided by x minus 4 over 7 is the same as 5 times 7 over x minus 4. So we get 35 over x minus 4 plus 2. We need a common denominator. So we get 35 over x minus 4 plus x minus 4 over 2 times x minus 4. So we can see here that this is not going to be x, not equal to x. So this is not an inverse of f of x. And then the third one that I added, we have p of x is equal to 7x plus 4. So if we find the composition, let me write f of x up here so we can see it. Then here we get p of f of x, which is x minus 4 divided by 7. So anywhere I see an x for p, I'm going to substitute the value in the parentheses. So simplify here, distribute this, so we get 7x minus 28 divided by 7 plus 4. And so we need a common denominator, which is going to be 7. So in order to make this 4 a 7, have a denominator of 7, I multiply the top and bottom by 7. 4 times 7 is 28. So we can see that negative 28 plus 28 is 0, giving us 7x divided by 7. So we get x. So p of f of x gives us x. So that is good because we are supposed to get an x. However, it has to work if we reverse it. So instead of p of f of x, we also have to check f of p of x. So here I have f, p of x is 7x plus 4. So anywhere I see an x for f, I'm going to plug in 7x plus 4. So for this x, I'm going to plug in 7x plus 4 minus 4 divided by 7. So 4 minus 4 is 0. So we end up with x. So you can see here, if we reverse the order of the functions, p composed of f of x or f composed of p of x, it doesn't matter, they both give us back an x. When that happens, then we say yes, it is an inverse of f of x. So yes, p of x is an inverse of f of x. Okay, so let's look at what happens with the graph. The graph of f and f inverse are related to each other in this way. If the point AB lies on graph f, so that's point AB, then the point BA must lie on the graph of the inverse and vice versa. This means that the graph of F inverse is a reflection of the graph of Y in the line Y equals X. So here this dotted line represents the line Y equals X, and it's a reflection. This function F is a reflection of the inverse, and you can see that AB is on this side and BA is on this side. So that happens with the graphs. So it says verify graphically that the functions f of x is equal to 4x minus 1 and g of x equals 1/4 x plus 1 are inverse functions of each other. So first we would have to graph f of x. You can use the y-intercept or you can use a table of values. Okay, and then for g of x, we have 1/4 x plus 1. We can do the same thing. So if we have our graphs, I'm going to use y equals mx plus b for this one. So we have -1 is your y-intercept. And then my slope is 4. So that means I'm going to go up 4. So 1, 2, 3, 4, and then to the right 1. Okay, so this is my line. And then for the second one, I'm going to go ahead and use a table of values. So if I use -1, 0, and 1, so here we get 1/4 plus 1/4 is 2/4, which is a half. So we plug in the 1 for x here. 1/4 plus 1 is 1/4 plus 1/4 gives us 2/4, which becomes a half. If I plug in 0 here, then I get 1/4. And if I plug in -1 here, I get -1/4 plus 1/4, which would be 0. And then I guess I can use a table of values here as well, so we can compare the values. If x is -1, we get -4 minus 1 is -5. If we plug in 0, we get -1. And if we plug in 1, we get 4 minus 1 is 3. Okay, so let me plot this one here. We get -1 and 0, 0 and 1/4, just somewhere here, and then 1 and 1/2. So this line would look something like this. Yeah, so let's look at the graph on the computer just to get a better view. So the first one is 4x minus 1. And then the second one is 1/4 divided by or times x plus 1. So look at the values there and think about whether these are inverses of each other or not. Okay, so if I was to draw the line y equals x, this is the green line here. Then if I choose a point 0, -1. Then notice here that -1 gives me 0, and 0 gives me -1. So we're switching the x and the y. So that means that these are going to be inverses of each other, and you can see the reflection on this green line. Okay, so I'm going to draw this as a dotted line. And so you can see the graphs reflect on this dotted line. So we say yes, they are inverses of each other. And again, you can pick a point like this one here, -1 and 0. This is for g of x, and f of x, it would be 0, -1, which is on the graph. Okay. So the next one, verify graphically that the functions f of x equals x squared plus 1, x greater than or equal to 0, and g of x equals x minus 1 are the inverses of each other. So we have f of x is equal to x squared plus 1, and they only want us to look at the values greater than 0. So if I was to graph this using the transformations that we learned in the previous section, then my graph looks something like this. However, they want us to consider only from the values x greater than or equal to 0. So that means that we're not going to include this side on the left side. Okay, so if I graph this, we're only looking at this point here. That goes like this. To help me, I just plot in another number, 1. 1 squared is 1 plus 1 is 2. Now this one here is the square root, and it's being shifted to the right. So I'm going to move over to the right one, and my graph will look something like this. Okay, so we want to know, are these inverses of each other? So remember, there's this y equals x dotted line, and this point here is 1, 0, and this point here is 0, 1. So we can see that the values are switched, x and y, 0, 1, and 1, 0. This has reflection on this line, so this is yes, they are inverses. Okay, the next one, a function f has an inverse if and only if no horizontal line intersects the graph of f at more than one point. A function is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. A function f has an inverse if and only if it's one-to-one. So this is what it means. So like here's your x, here's your y. 1, 2, 3, 4, 5, 6. It's one-to-one if the x's are going to exactly one y. In other words, the y's aren't repeated in this case as well. But there is a horizontal line test that we can use. If you draw a horizontal line and it only touches a graph at one point, then we say that the graph has an inverse. So first, we need to make sure that it's a function. So to determine if it's a function, we actually draw a vertical line test. And the vertical line test here shows that it only crosses in one point. So this is a function, and it has an inverse. So for the circle here, first we check for a function. So if I draw a vertical line test, it touches in two places. So this is not a function. If it's not a function, then it's not an inverse, or it's not going to have an inverse. Does not have inverse. And then number 3, if I draw a vertical line test, this is a function. So if it has an inverse, we check with a horizontal line test, and notice that it touches in 2 places. So that means that it does not have inverse. Okay, the last part of this is basically how do we find this inverse. So first we're going to use the horizontal line test to decide whether it has an inverse. And then we're going to replace f of x with y, interchange the rows, and then solve for the y. So this is a line. That means that no matter if the line is like this, if you draw a horizontal line, it is going to be a function. If you draw a horizontal line, then it's going to have an inverse. To find the inverse, we let y, f of x equals to y. That's the first step. The second step is we're going to interchange x and y. So instead of y here, I write x. And then I have 2y plus 7. And now you want to solve for y. So we get x minus 7 is equal to 2y divided by 2. So y is equal to 1/2 x minus 7/2. Okay, so our last step here is to rewrite y. Instead of saying y, we're going to write it as the inverse. And that's equal to 1/2 x minus 7/2. Okay, so let's try the next one. First step, let g of x, call it y. Then we're going to switch x and y. Then we're going to solve for y. Divide by 4. So we get x plus 1 divided by 4 is equal to y cubed. Take the cube root. So y is equal to the cube root of x plus 1 divided by 4. So if this does have an inverse, this would be our answer. So we need to check the graph. Let me go ahead and plot it over here on decimals to see if it passes the horizontal line test. And you can see if you draw a horizontal line, then it's going to be a function, meaning that it has an inverse, or it could have an inverse. It doesn't necessarily have one. It might or it might not have one, but at least we know that if it's a function, then we can look for the inverse. So here we have f inverse of x is equal to the cube root of x plus 1 divided by 4. Okay, let's look at letter H. I'm going to go ahead and graph it. So if I graph this, I get 5 minus 3x divided by x plus 2. So if we draw a horizontal line, it's only going to cross in one place. So that means we can find the inverse. So I'm going to let this be equal to y. Then we need to switch them. So anywhere I see an y, replace it with x. And anywhere I see an x, I replace it with y. And then we're going to solve for y. So I'm going to multiply both sides by y plus 2. So I end up with y plus 2 times x is equal to 5 minus 3y. I'm going to distribute the x here. So y times x is yx, 2 times x is 2x. We want to have all the y's on one side. So I'm going to add 3y. And I'm going to subtract the 2x on both sides. So now here they have income in a y, so I can factor out a y. So if I take y out, I get an x, and if I take y out, I get 3. Divide by x plus 3. So y is equal to 5 minus 2x, x plus 3. So my inverse is 5 minus 2x, x plus 3. Example 9, use the graph to draw the inverse. So here, first, we can look at the graph for f of x, get the ordered pairs. So this point is -3, -2. This point here is -2 and 2. And then this point here is 4 and 1. Since we're looking for the inverse, I can switch these order pairs. So instead of -3, -2, I can write -2, -3, 2, -2, and 1, 4. So -2 and -3 is right here. 2 and -2 is right here. And 1 and 4 is up here. So my graph will look like this. Okay. So that is the end of section 1.9.